The universe rotates. Every atom, every star, every galaxy spins in this endless cosmic dance. The Earth completes a revolution around its axis. The Sun rushes in an orbit around the center of the galaxy. The galaxy itself twists into a spiral. And do you know what is most striking? No one really knows why this is happening. We have become so accustomed to rotation that we have stopped asking the most important question. And why, actually, does everything spin? Why does the universe not stand still? Why did it choose this particular dance instead of immobility? Physicists will tell you about angular momentum and its conservation. Astronomers will tell you about the collapse of gas clouds. But here is what is interesting. If you dig deeper, it turns out that we still cannot explain where the very first rotation came from. That rotation that launched this entire cosmic waltz. Moreover, recent studies show that even the universe itself might be rotating. Imagine not just the galaxies inside it, but the entire universe as a whole makes one slow, majestic revolution. And this revolution is so long that it takes more time than humanity has existed. Today, we will set off on a journey from the quantum foam of the first moments after the Big Bang to modern galactic superstructures. We will learn why planets cannot stop even if they want to, how Venus managed to spin in the opposite direction, and what a figure skater on ice and a collapsing cloud of gas have in common. Get ready for your perception of space to change forever. Let us start from the very beginning. From those times when people first raised their eyes to the sky and noticed that the stars do not just shine, they move. Ancient observers, having neither telescopes nor computers, managed to see the main thing. The sky rotates. Every night, the stars describe circles around one point. In the northern hemisphere, this point is near the North Star. In the southern hemisphere, there is no such bright star. But the point is there, and around these points, the entire celestial vault completes a majestic revolution in 24 hours. The ancient Greeks were certain that it was the celestial sphere to which the stars were attached that rotated. A huge crystal dome spins around the immobile Earth. Aristotle, the greatest mind of his time, built an entire cosmology on this idea. In his model, the sky consisted of many spheres nested inside each other. Each planet sat on its own sphere. All of them rotated, set in motion by a divine prime mover. The system was beautiful, logical, and completely wrong. But here is what is striking. Even being wrong in the details, this model captured the main thing. Indeed, rotation is everywhere. It is just that it is not the sky rotating around the Earth, but the Earth rotating around its axis. Copernicus, when he decided to turn cosmology upside down by placing the sun in the center, faced the same question. Fine. The Earth rotates around the sun, but why? What makes it move in orbit, and why does it spin around its own axis? Tycho Brahe, the greatest observer before the telescopic era, spent his whole life measuring the positions of the planets with incredible precision. He noticed that planets do not move just in circles. Their trajectories are more complex. Mars sometimes speeds up, then slows down, then approaches the Earth, then moves away. And Brahe could not understand why. The answer was found by his student Johannes Kepler. After spending years in calculations and going through dozens of models, Kepler came to a radical idea. The orbits of planets are not circles, but ellipses, and the sun is not in the center of this ellipse, but in one of its foci. This was a breakthrough. Suddenly, all the oddities in the movement of planets made sense. When a planet approaches the sun, it speeds up. When it moves away, it slows down. Everything obeys strict mathematical laws. Kepler derived 3 laws of planetary motion. The first law spoke of elliptical orbits. The second explained why planets change speed. A radius vector connecting a planet to the sun sweeps out equal areas in equal intervals of time. It sounds complicated. Imagine that you tied a stone to a rope and spun it over your head. When the stone is further from your hand, it moves slower. When it is closer, it moves faster. In the same way, planets fly faster closer to the sun and slow down further from it. Kepler's third law connected the orbital period of a planet with the size of its orbit. The further a planet is from the sun, the slower it moves and the longer its year lasts. Mercury, the closest to the sun, rushes like one possessed and makes a revolution in 88 Earth days. Neptune, on the outskirts of the system, completes a circle in 165 Earth years. These laws worked flawlessly, but they described how, not why. Why do planets move at all? What pushes them? Kepler thought it was some kind of magnetic force emanating from the sun. He imagined that the sun radiates streams of an invisible substance that rotates the planets, like a mill wheel is rotated by water. The idea was close to the truth, but not quite correct. The truth was discovered by Isaac Newton. Sitting in a garden, he saw an apple fall from a tree, and it dawned on him. What if the same force that pulls the apple to the Earth keeps the moon in orbit? What if gravity is universal? What if it acts not only between the Earth and the apple, but between any two bodies in the universe? Newton formulated the law of universal gravitation. Every body attracts every other body with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. It sounds like a spell, but in fact, it means a simple thing. The more massive an object, the stronger it attracts. The further objects are from each other, the weaker the attraction. Double the distance, and the force will drop 4 times. Triple it, and it will weaken 9 times. From this law, Newton mathematically derived all 3 of Kepler's laws: elliptical orbits, change in speed, the connection of the period with the distance. All of this turned out to be a consequence of universal attraction. Planets move in orbits not because something pushes them, but because they are falling toward the sun, but falling in a special way. Imagine that you throw a stone horizontally. It flies forward, but simultaneously falls down. If you throw it hard enough, it will fly so far that the curvature of the Earth will become noticeable. The Earth will, as it were, move out from under the stone. Throw even harder, and the stone will fall as fast as the surface of the planet curves. It will never fall. It will go into orbit. This is exactly what the planets do. They are continuously falling toward the sun, but thanks to their speed, they miss it. Newton explained orbital motion, but the question remained, why do planets rotate around their axes? The Earth completes a revolution in 24 hours. Jupiter, despite its giant size, manages to turn in 10 hours. Mars spins at about the same speed as the Earth. Venus barely crawls, completing a revolution in 243 days, and it spins in the opposite direction. What kind of chaos is this? The solution did not come immediately. It took another 2 centuries of observations, theoretical calculations, and debates. And the key was the understanding of one fundamental law of nature, the law of conservation of angular momentum. This law is so important to our story that it is worth looking into it in more detail. Remember the figure skaters on ice. When a skater rotates with arms spread to the sides, they spin slowly, but as soon as they press their arms to their body, the rotation speeds up, and it speeds up dramatically. The athlete can turn into a blurred spot rotating at an incredible speed. What happened? Where did the energy for acceleration come from? The secret is that the total amount of rotational motion, or angular momentum, is conserved. This is one of the fundamental properties of our universe. If no external forces act on a system, the angular momentum remains constant. The skater, by pressing their arms, reduces the distance from the mass of their body to the axis of rotation. And angular momentum depends not only on the speed of rotation, but also on the distribution of mass. The more compact the mass, the faster the rotation must be for the angular momentum to remain the same. This same principle works in the universe. A cloud of gas in space rotates slowly, very slowly, so slowly that one revolution can take millions of years. But then the cloud begins to shrink under the action of its own gravity. Gas particles move toward the center. The distance from the axis of rotation decreases, and the cloud begins to spin faster, much faster. By the time a star is formed from the cloud, the rotation has accelerated millions of times. A young star rotates so fast that it can complete a revolution in a few days or even hours. The sun, by the way, rotates relatively slowly. One revolution takes about 25 days at the equator and a little over 30 at the poles. Yes, the sun rotates at different speeds at different latitudes because it is not a solid body but a gas sphere. Now for the most important question. Where did the rotation of the original cloud come from? Why did it spin at all, even if slowly? Here we come to the very essence of the problem, to what physicists are still trying to understand completely. The answer lies at the very beginning, in the first moments after the Big Bang. 13 billion years ago, the entire observable universe was compressed into a point, not into a small ball, but precisely into a mathematical point of zero size. At this point, the density and temperature were infinite. Space, time, matter, energy, everything was compressed into a singularity. And then this point exploded, not in space, but together with space. Space itself began to expand. It is impossible to imagine this because our brain is used to explosions happening in already existing space. But here, space itself was what was expanding. There was no outside. There was only the expanding universe. In the first fractions of a second, the universe was incredibly hot and dense. The temperature exceeded trillions of degrees. Particles of matter and antimatter were born and destroyed in a mad dance. Quarks, electrons, photons, neutrinos. All of this was boiling in a primordial soup. And in this chaos, there were already tiny inhomogeneities. Quantum fluctuations, places where the density was slightly higher and places where it was slightly lower. These fluctuations were microscopic. The differences in density were fractions of a percent, but they were uneven not only in space but also in time. Some regions expanded slightly faster, others slightly slower. And from these tiny differences, rotation was born. Imagine a large whirlpool in the ocean. Where does it come from? From the collision of currents. One current moves in one direction, another in the other. At their boundary, a swirl forms. The water begins to twist. In the early universe, something similar happened. Different regions expanded at different speeds and in slightly different directions. At the boundaries, swirls arose, not of water, but gravitational ones. These primary swirls were the seeds of all future rotations. From them grew rotating galaxies, from galaxies rotating stellar systems, from systems rotating planets. The entire cosmic dance began with tiny quantum tremors in the first moments after the Big Bang. But there is something else. Recently, astronomers discovered a strange thing. It turned out that galaxies do not rotate completely randomly. If you take a large sample of galaxies and look at which way they are twisted, clockwise or counterclockwise as seen from Earth, you find a weak but statistically significant asymmetry. There are slightly more galaxies twisted in one direction than in the other. The difference is only a couple of percent, but it is there. This puzzled scientists. If the universe is isotropic, that is, the same in all directions, then there should be no asymmetry. Galaxies should twist in both directions with equal probability. No facts are stubborn things. There is a symmetry, and the only explanation that comes to mind is that the universe itself rotates. Not the galaxies in it, but the entire universe as a whole. Moreover, it rotates very slowly, so slowly that one revolution takes hundreds of billions of years. This is much older than the age of the universe itself. We live in an era when the universe has not yet had time to turn even a small fraction of a full circle. But the rotation is there, and it sets a preferred direction for the rotation of galaxies. How is this possible? How can the entire universe rotate? Relative to what does it rotate if there is nothing outside? This is a deep philosophical and physical question. Some physicists suggest that our universe was born from a black hole in another universe and inherited angular momentum from that mother universe. Black holes rotate. If our universe is the interior of a black hole, then it must also rotate. It sounds crazy, but the mathematics works. The equations of general relativity allow for such solutions. A rotating universe born from a rotating black hole. This explains not only rotation, but also a number of other mysteries. For example, why dark energy, which accelerates the expansion of the universe, is gradually weakening. In the model of a rotating universe, dark energy is simply a centrifugal force, and centrifugal force weakens as the rotation slows down. Of course, this is only a hypothesis. It is impossible to prove it yet, but the very fact that we can formulate and test it shows how far science has advanced. We ask questions that our ancestors could not even imagine. Does the universe rotate? What was before the Big Bang? Does a multiverse exist? But let's return to more tangible things, to the galaxies. These giant islands of stars are scattered throughout the universe. There are trillions of them in the observable part of space. Most galaxies rotate, and they rotate so fast that it creates a serious problem for physicists. Take our galaxy, the Milky Way. It is a disk with a diameter of about 100,000 light-years. In the center is a core, a dense cluster of stars and a supermassive black hole. Spiral arms extend from the core, where young stars are born. The Sun is in one of these arms, about 26,000 light-years from the center. The galaxy rotates, but it does not rotate like a solid body. If the Milky Way were a vinyl record, all points on it would rotate with the same angular velocity. The outer edge would move faster than the inner part, but would complete a revolution in the same time. In a galaxy, everything is different. Stars closer to the center move faster than those on the outskirts. The Sun rushes in its orbit at a speed of about 200 kilometers per second and completes a full revolution around the center of the galaxy in about 200 million years. This is called a galactic year. During the existence of the Earth, our planet has flown around the center of the galaxy only 20 times. But here is what is strange. According to Newton's laws, the speed of stars in orbits should fall as they move away from the center, like planets in the solar system. Mercury flies faster than the Earth faster than Mars faster than Jupiter. The logic is simple. The further from the source of gravity, the weaker the attraction, the slower the orbital speed should be. Galaxies do not obey this logic. Astronomers measured the speeds of stars at different distances from the center of the Milky Way and found that the speed almost does not change. Stars on the outskirts of the disk move about as fast as stars closer to the center. The rotation curve of the galaxy turned out to be flat, not falling. This was a shock. If the speed does not fall, it means there is additional mass on the outskirts of the galaxy, mass that we do not see. It must be distributed throughout the entire volume of the galaxy, forming a huge halo. And the mass of this invisible halo must be much greater than the mass of all visible stars and gas combined. Thus, dark matter was discovered, or rather, suspected. There is still no direct proof of its existence. No one has ever seen a particle of dark matter. No indirect evidence is irrefutable. Galaxies rotate as if they have 10 times more mass than we observe. Clusters of galaxies are held together by the gravity of invisible matter. Gravitational lensing, the bending of light from distant objects, shows that there are huge masses in space that we cannot see directly. Dark matter does not emit light. It does not interact with electromagnetic radiation at all. It does not reflect photons, does not absorb them, does not emit them. The only way it manifests is through gravity. Dark matter attracts ordinary matter, bends space, influences the movement of stars and galaxies, but it is impossible to see it. What is it? What particles make up dark matter? Why is it invisible? Physicists do not yet have an answer to these questions. Many hypotheses have been put forward. Some suggest these are exotic particles, WIMPs or axions, which almost do not interact with ordinary matter. Others believe that dark matter consists of primordial black holes formed in the first moments after the Big Bang. Still others suggest modifying the laws of gravity so that dark matter is not required at all. But the fact remains. Whatever dark matter is, it is what determines the rotation of galaxies. It is what forms the structure of the universe. Visible matter, stars, planets, gas, dust, people, is just foam on the surface of the ocean, and the ocean itself consists of dark matter. And this invisible substance plays a key role in the formation of rotating structures. When the universe began to cool after the Big Bang, the clumps of dark matter were the first to condense. They did not interact with light, did not scatter under radiation pressure. They simply gathered under the influence of gravity and formed giant halos, and then ordinary matter fell into these halos. Hydrogen and helium left over from the Big Bang were pulled to the clumps of dark matter, swirled into disks, and gave birth to stars. Without dark matter, galaxies simply would not have formed. There was not enough ordinary matter to overcome the expansion of the universe and gather into compact structures. Dark matter provided the gravitational wells in which visible matter could condense. Dark matter was the scaffolding on which the entire observable universe arose. And one more important detail. Dark matter does not just attract ordinary matter. It transfers angular momentum to it. The dark matter halo itself rotates, and when gas falls into this halo, it picks up the rotation, like water swirling into a drain. Gravity pulls the gas to the center, but the angular momentum prevents it from falling directly. The gas swirls into a disk, and in this disk, stars begin to form. The process of stars being born from gas clouds is one of the most beautiful in the universe. Take a typical molecular cloud, huge, cold, dark. The size can reach hundreds of light years. The mass is tens or hundreds of thousands of times the mass of the sun. The temperature is about 10 degrees above absolute zero. In such a cloud, gas molecules move very slowly, and the cloud rotates slowly. One revolution can take millions of years. But then at some point, the equilibrium is disturbed. Maybe a supernova exploded nearby and the shock wave compressed the cloud. Maybe two regions of the cloud collided, or simply the cloud became massive enough for its own gravity to start pulling matter to the center. Collapse begins. At first, it is slow. The gas is compressed, the density grows. The temperature does not rise yet because the cloud is transparent to infrared radiation. Energy freely goes into space, but as the density increases, the cloud becomes more and more opaque. Radiation begins to be trapped inside, and the temperature rises. And here the most interesting part begins. The cloud rotated slowly, but as it shrinks, the rotation speeds up. Remember the figure skater? The same effect. Gas particles approach the axis of rotation. Angular momentum must be conserved, so the angular velocity grows. By the time the density in the center of the cloud becomes high enough, the rotation accelerates millions of times. The central region can no longer shrink further because centrifugal force opposes gravity. The cloud flattens out and turns into a disk. In the center of the disk, a protostar is formed, and a protoplanetary disk rotates around it. This disk is the cradle of planets. The entire planetary system will emerge from it. But before we move on to planets, let's look at the protostar itself. It is not yet a real star. Thermonuclear reactions have not yet begun in its center. It is just a hot clump of gas that continues to shrink and heat up. The protostar rotates fast, very fast. Young stars can complete a revolution in a few hours. This creates a problem. If the star rotates too fast, centrifugal force can tear it apart. Matter at the equator will be thrown into space. the star will not be able to hold itself together. Nature solves this problem in an elegant way. The star gets rid of excess angular momentum through a magnetic field and stellar wind. Young stars have a powerful magnetic field. This field is coupled with the protoplanetary disk, and through this coupling, angular momentum is transferred from the star to the disk. The star slows down, the disk speeds up and expands. Simultaneously, the star begins to emit a powerful stellar wind. A stream of charged particles bursts out of the star's atmosphere and is carried into space. These particles move along the lines of the magnetic field, and, as they move away from the star, they carry away angular momentum with them, like water flowing out of a rotating sprinkler. After several million years, the star slows down to a reasonable speed. The Sun, for example, rotates with a period of about 25 days. This is slow compared to young stars, but still fast by human standards. And the Sun continues to slow down slowly. In billions of years, it will rotate even slower. And what happens to the protoplanetary disk? This disk is an amazing structure, flat, rotating, full of gas, dust, and emerging planets. At first, the disk is very hot. The substance in it is heated to 1,000 degrees, but gradually it cools. The gas radiates energy into space, the temperature falls, and the process of condensation begins. Closer to the star, where it is hot, only refractory substances condense, silicates, metals. They form solid dust particles the size of a grain of sand. These dust particles collide with each other, stick together, and grow. First, pebbles the size of gravel appear, then boulders, then planetesimals, bodies the size of an asteroid. Further from the star, beyond the so-called snow line, it is cold enough for volatile substances to condense, water, ammonia, methane. They freeze and also form solid particles. There is much more material for building planets here. Planetesimals grow faster and reach a critical mass sufficient to start attracting gas from the disk. Thus, gas giants are born. A solid core with a mass several times that of the Earth attracts hydrogen and helium from the surrounding disk. Gas collapses onto the core, a massive atmosphere is formed, and the planet grows. Jupiter and Saturn grew this way. They consist mainly of gas, but stone ice cores are hidden in their centers. Closer to the star, where there is less gas and the temperature is higher, terrestrial planets are formed: Mercury, Venus, Earth, Mars. They are small, solid, and consist mainly of silicates and metals. They may have an atmosphere, but it is thin compared to the atmospheres of the giants. And all these planets rotate because they were formed from a rotating disk. When planetesimals collided and stuck together, they transferred angular momentum to each other. On average, the angular momentum was added up. Most collisions happened at an angle, not head-on, and each such collision added rotation to the planet. By the time the planet grew to its final size, it was already rotating fast. The Earth in its youth rotated much faster than now. A day lasted only 6 hours. Jupiter, despite its huge mass, makes a revolution in 10 hours. Saturn is a bit slower, but also fast. Even tiny Mercury once rotated fast, although now it has almost stopped due to tidal breaking. The rotation of planets is determined by the history of their formation. The direction of rotation, the speed, the tilt of the axis, all of this is the result of countless collisions in the protoplanetary disk. In most cases, planets rotate in the same direction as the entire system. They spin counterclockwise if viewed from the North Pole of the Sun. This is not a coincidence. This is the legacy of the protoplanetary disk, which rotated in this direction. No, there are exceptions, and these exceptions tell their own dramatic stories, of collisions that flipped planets, of tidal forces that stopped rotation, of the chaos of the young solar system when planets had not yet occupied their final orbits and were bombarded by asteroids. Venus is the strangest planet in the solar system, not because it is hot, although the temperature on its surface melts lead, not because its atmosphere is dense as water, although the pressure at the surface would crush any terrestrial craft, but because it rotates differently than all the others. All planets in the solar system spin counterclockwise if viewed from the North Pole of the Sun. Earth, Mars, Jupiter, Saturn all inherited this direction from the protoplanetary disk. But Venus decided to do otherwise. It rotates clockwise, in the opposite direction, and very slowly. One revolution takes 243 Earth days. This is more than the Venusian year, which lasts only 225 days. An absurd situation arises. A year on Venus is shorter than a day. The planet manages to fly around the Sun faster than it turns around its axis. If you stood on the surface of Venus and watched the Sun's movement across the sky, you would notice a strange thing. The Sun rises in the west and sets in the east. Everything is the other way around. What happened to Venus? Why does it spin this way? For a long time, the main hypothesis was a giant collision. Scientists assumed that in Venus's youth, a large body, the size of Mars or even larger, collided with it. The impact was so powerful that it flipped the planet. It literally tumbled in space. But there is a problem with this hypothesis. If the impact was strong enough to flip the planet, it should have heated it to incredible temperatures. The energy of the collision would have turned into heat. The entire crust of Venus would have melted. The planet would have become a ball of molten lava. And traces of this cataclysm should have been preserved. But the geological history of Venus does not show signs of such an event. Moreover, if Venus were flipped by an impact, its moons, if it had any, should have acquired strange orbits. But Venus has no moons at all. This is a mystery in itself. Modern researchers lean toward a different explanation. The atmosphere is to blame. Venus's atmosphere is incredibly dense and massive. It is 90 times denser than Earth's. And this atmosphere has a strange property. It rotates much faster than the planet itself. The upper layers of the Venusian atmosphere fly around the planet in 4 days. This phenomenon is called superrotation. Winds at an altitude of 50 kilometers rush faster than an airplane. They create a giant vortex structure encircling the entire planet. And this structure interacts with the surface through tidal forces. The sun heats the atmosphere unevenly. The day side heats up. The night side cools down. In the dense atmosphere, powerful tides arise. Not water tides, but air tides. These tides pull the surface of the planet along. Very slowly, over billions of years, they slowed Venus's rotation, stopped it, and then accelerated it in the opposite direction. It is like the story with the figure skater, only in reverse. Instead of shrinking and accelerating, Venus expanded its atmosphere and slowed down. Angular momentum flowed from the solid planet to the gas envelope, and the atmosphere now rotates fast, while the planet rotates slowly. But Venus is not the only oddity. There is also Uranus, the 7th planet from the Sun, an ice giant on the outskirts of the system. Uranus does not just rotate in the opposite direction, it rotates lying on its side. Its axis is tilted by almost 100 degrees. This means that Uranus's north pole is pointed where other planets have their equator. Imagine that you spun a top. Usually, a top stands vertically and spins around a vertical axis. Now imagine a top that lies on its side and spins horizontally. This is what Uranus looks like. It rolls along its orbit like a wheel, rather than rotating like a top. This creates absurd seasons. On Uranus, a year lasts 84 Earth years. And during this year, each pole in turn is pointed directly at the Sun for 42 years. 42 years of continuous day at one pole, 42 years of continuous night at the other. Then they swap places. What happened to Uranus? Why is it on its side? The classic hypothesis, again, is a collision. In the youth of the solar system, when planets were still forming and migrating in orbits, a body the size of the Earth or even several bodies collided with Uranus. A series of impacts overturned the planet. But here, too, there are problems. Uranus's moons rotate in the same plane as the planet's equator, meaning their orbits are also tilted. If Uranus were overturned after the moons formed, their orbits would have remained in the original plane, but they changed along with the planet. How is this possible? Recently, a new hypothesis appeared. The culprit is not a collision, but a giant ring system. In its youth, Uranus could have had rings much more massive than now. These rings rotated in the plane of the planet's equator, and they created tidal forces that rocked Uranus's axis of rotation. Like a top rocks when it begins to lose speed. Its axis starts describing circles. This is called precession. Young and fast-rotating Uranus experienced axis precession, and massive rings amplified this effect. Gradually, over millions of years, the axis tilted further and further until it lay almost horizontally. Then the rings were destroyed or shed. Only the modern thin rings that we observe remained. No, the axis tilt was preserved. Uranus continues to roll along its orbit like an eternal monument to the chaos that reigned in the young solar system. Mercury represents another type of anomaly. It rotates normally, in the same direction as all other planets, but very slowly. One revolution takes 59 days, and a year on Mercury lasts 88 days. The planet is in a strange resonance. For every 2 revolutions around the Sun, it makes exactly 3 revolutions around its axis. This is not a coincidence. It is the result of tidal breaking. Mercury is very close to the Sun. The star's gravity creates tidal deformations in the body of the planet, just as the Moon creates tides on Earth. And these deformations break Mercury's rotation. Once Mercury rotated fast, but the tides slowed it down. The planet fell into a resonance where tidal forces reach a minimum. And now Mercury is stuck in this state. It will not stop completely, like the Moon, which is always turned to the Earth with one side, but it will not rotate fast either. The resonance is stable. All these anomalies show an important thing. The rotation of planets is not something frozen, it changes. Tidal forces slow down rotation. Atmospheres can flip planets. Collisions change the tilt of the axis. Rotation is a dynamic process that continues for billions of years. Look at the Earth. Our planet is also slowing down, very slowly but steadily. The Moon is to blame. The Moon creates tides in Earth's oceans. The water rises and falls twice a day, and this movement of water creates friction against the bottom of the seas and oceans. Friction takes energy from Earth's rotation. The planet slows down. Every year, the day becomes longer by a tiny fraction of a second, so tiny that during a human life it is impossible to notice. But over millions of years, the difference accumulates. In the era of the dinosaurs, days were shorter. The year consisted not of 365 days, but of 400. In a billion years, a day on Earth will last not 24 hours, but 30 or 40. The planet will rotate much slower. Ultimately, if nothing interferes, the Earth will stop completely. It will always be turned to the Moon with one side, just as the Moon is now turned to the Earth. No, there is an interesting detail. While the Earth is braking, the Moon is accelerating. Or rather, it does not accelerate in the usual sense, but moves away from the Earth. Every year, the Moon moves away from us by several centimeters. This seems insignificant, but over geological times, the distance increases substantially. When the Moon formed, it was much closer to the Earth, perhaps 10 times closer than now. It hung in the sky as a huge disk, occupying a significant part of the sky. The tides were monstrous. Ocean waters rose by hundreds of meters. Earth's rotation was frantic. A day lasted only 6 hours. Gradually, the Moon moved away, the tides weakened, and Earth's rotation slowed. The process continues now, and it obeys a fundamental law, the law of conservation of angular momentum in the Earth-Moon system. When the Earth loses angular momentum due to tidal breaking, this momentum does not disappear. it passes to the moon. The moon receives additional angular momentum. And in celestial mechanics, there is a paradoxical rule. When a body in orbit receives angular momentum, it does not speed up, but slows down and moves away. It sounds strange. Imagine that you tied a stone to a rope and are spinning it. If you give the stone extra speed, it will fly further. But in space, everything is different. Additional energy moves the body to a higher orbit, and in a higher orbit, the speed is lower. The moon moves in its orbit slower than before, but the distance to the Earth is greater. This process has an end. Theoretically, in tens of billions of years, the Earth and Moon will be in a fully synchronized state. The Earth will always be turned to the Moon with one side. The Moon, as now, will always show the Earth one hemisphere, and both will complete a revolution around their axes in the same time it takes the Moon to fly around the Earth. The system will freeze in a gravitational embrace, but this will not happen. Long before the Earth and Moon reach such a state, the Sun will turn into a red giant and swallow both. Tidal breaking is a slow process, too slow for the short cosmic lives of stars and planets. Nevertheless, this process is fundamental. It works everywhere. All satellites in the solar system that are close enough to their planets are turned to them with one side. The Moon to Earth, Phobos to Mars, the moons of Jupiter to Jupiter. This is not a coincidence. It is the result of tidal breaking acting for billions of years. And what about dark matter? How does it affect rotation? We already said that dark matter forms a halo around galaxies, and this halo determines how fast stars rotate at different distances from the center. But dark matter's role is deeper. Dark matter is not just a passive mass that attracts ordinary matter. It is an active participant in the cosmic dance. The dark matter halo rotates, and this rotation is transferred to visible matter. When gas falls into the halo, it swirls, forms a disk, and from the disk, stars are born. And all this rotation initially came from dark matter. Moreover, the distribution of dark matter affects the stability of galactic rotation. Without the dark halo, the spiral arms of galaxies would quickly unwind. Differential rotation, the fact that the inner parts of the galaxy rotate faster than the outer parts, should have destroyed the spiral structure in a few revolutions. But spirals have existed for billions of years. Why? Because dark matter stabilizes them. The gravity of the dark halo creates density waves that propagate through the galactic disk. These waves form the spiral arms. The arms do not rotate together with the stars. They stay in place, and stars pass through them like cars driving through a traffic jam. In the spiral arms, the gas density is higher. There, clouds are compressed and new stars are born, massive, bright blue ones. These stars do not live long, a few million years, but they are bright enough to light up the spiral arm. Therefore, spirals look blue in photographs of galaxies. This is not because there are more stars there, but because young hot stars are born there. And dark matter conducts this entire process. It sets the pace, determines where and when density waves will arise, and forms the structure of the galaxy at a deep level. We see only the tip of the iceberg, glowing stars, while beneath the surface hides a huge mass of dark matter that controls the motion. Recently, astronomers discovered another amazing fact. The central bar of the Milky Way, a region of densely packed stars in the shape of a rod, is slowing down. It rotated faster in the past, and now its rotation is being braked, and the culprit, as you already guessed, is dark matter. The bar interacts with the dark matter halo through gravity. This interaction creates friction, not ordinary mechanical friction, but gravitational. The bar transfers its angular momentum to the dark halo and slows down. The process is slow but steady. During the time of the galaxy's existence, the bar has lost a quarter of its rotation speed. This discovery is important because it gives us a new way to study dark matter. We cannot see it directly, but we can see its influence on the rotation of galactic structures. By measuring how the bar slows down, we can estimate the mass and distribution of dark matter in the Milky Way's halo. And here is what is interesting. It turns out there is much more dark matter in the galaxy than we thought. Previous estimates gave a ratio of about 10 to 1, 10 parts dark matter to 1 part ordinary matter. New data show the ratio is closer to 20 or even 30 to 1. We live not just in a galaxy of stars, we live in a cloud of dark matter that is 30 times more massive than everything we can see. This thought changes perspective. The universe we observe, stars, galaxies, nebulae, planets, is a thin film on the surface of an invisible ocean, an ocean of dark matter. And it is this ocean that determines the structure of the cosmos. It was what created the conditions for the formation of galaxies, for the birth of stars, for the appearance of planets, for the emergence of life. Without dark matter, galaxies would not have formed. After the Big Bang, ordinary matter was not enough to gather into compact structures. The expansion of the universe carried matter in different directions. The gravity of ordinary matter was too weak to stop this expansion on small scales. But dark matter began to condense earlier. It did not interact with light, did not scatter under radiation pressure. It simply gathered under the influence of gravity, formed clumps, and these clumps attracted ordinary matter. Hydrogen and helium fell into the gravitational wells created by dark matter, swirled into disks, and gave birth to stars. The first galaxies appeared several 100 million years after the Big Bang. These were small, irregular galaxies, but they rotated. Even then, rotation was a fundamental property of galaxies. And this rotation came from dark matter, from the primary swirls that arose in the early universe. Over time, small galaxies collided and merged. Larger structures formed, spiral galaxies, elliptical galaxies, giant galaxies in the centers of clusters, and all of them rotated. Every merger added angular momentum. Every interaction redistributed rotation between different components. The Milky Way grew exactly like this. It swallowed dozens of small galaxies. Some of them we can still see as streams of stars pulled by the tidal forces of our galaxy. These streams rotate around the center of the Milky Way, but in different planes and at different angles. They remember their former orbits from when they were part of independent galaxies. And now another merger is happening. The Milky Way is approaching the Andromeda Galaxy. Two giant spiral galaxies are moving toward each other at a speed of more than 100 kilometers per second. In 4 billion years, they will collide. The collision will be grand. The galaxies will pass through each other. Stars will not collide. Distances between them are too great, but gravity will mix both galaxies. The spiral arms will be destroyed, and gas clouds will collide and give birth to a burst of star formation. The sky will be full of young, bright stars. Then the galaxies will diverge again, turn back, and collide a second time, and a third. With each pass, they will lose energy, and the orbits will get closer. Finally, 1 billion years after the first collision, the galaxies will merge and form one huge elliptical galaxy. And this new galaxy will rotate. Its rotation will be the sum of the rotations of the Milky Way and Andromeda. The direction of rotation, the speed, the shape, all of this will be determined by how exactly the merger happens, at what angle the galaxies collide, how offset their centers will be, what the relative speed will be. But one thing can be said for sure: the rotation will not disappear. Angular momentum will be conserved. The new galaxy will spin as its predecessors spun. As all galaxies in the universe spin, rotation is eternal. It is not created or destroyed, only transferred, redistributed, transformed. Think about it. Every rotation we observe is an echo of that first moment, that moment when quantum fluctuations in the early universe gave birth to the first swirls. These swirls grew into galaxies. Galaxies gave birth to stars. Stars created planets. And on one of these planets, life arose. We ourselves, our bodies, consist of atoms that were once part of rotating gas clouds. These clouds collapsed into stars. Stars synthesized heavy elements, exploded as supernovae, threw matter back into space, and this matter gathered again into a cloud that swirled, formed the solar system, and gave birth to the Earth. Every carbon atom in your body was inside at least one star, possibly several. Every iron atom in your blood was born in a supernova explosion. The oxygen you breathe, the calcium in your bones, the phosphorus in your DNA, all of this came from stars. And all these stars rotated. Rotation is not just movement, it is memory. A memory of the origin, of the chaos from which order was born, of those first moments when the universe was just beginning its existence. Every rotating galaxy carries the imprint of those ancient times. Every star keeps angular momentum inherited from the protostellar cloud. Every planet spins because the protoplanetary disk once rotated, and this rotation will continue in billions of years. When the sun goes out and turns into a white dwarf, the Earth will still be rotating slower than now. Maybe it will have already stopped relative to the moon, but relative to the stars, it will continue its movement in orbit, falling around the cooling sun again and again endlessly. In trillions of years, when the last stars in the universe go out, galaxies will still be rotating, in the dark, without light, without heat. Black holes will slowly evaporate through Hawking radiation, but while they exist, they will spin, preserving the angular momentum of the stars that gave birth to them. Even at the very end, when the universe reaches maximum entropy and heat death occurs, rotation will remain. Individual particles will move chaotically, but in this chaos, the memory of the order that once existed will be preserved. Angular momentum is a quantum quantity. It cannot simply disappear. It is as fundamental as energy or mass. Rotation is eternal, eternal as the universe itself. It was in the beginning, it will be in the end. It is there now, in every atom, in every star, in every galaxy. The universe is a giant dance of rotating objects, and we are part of this dance. The Earth rotates under your feet. You do not feel it because you move along with the planet, but rotation is there. Every second, you are carried through space at a speed of more than 1,000 kilometers per hour at the equator. You fly around the Earth's axis once a day, fly around the sun once a year, fly around the center of the galaxy once every 200 million years. And the galaxy itself moves. It is falling toward the Virgo cluster along with the entire local group of galaxies. The local group rotates around a common center of mass. The Virgo cluster rotates. The Laniakea supercluster, which includes the Virgo cluster, also has a general rotation. The movements overlap each other. Like waves on the surface of the ocean, small ripples from the wind are superimposed on large waves from the surf. The surf is superimposed on the tidal wave on the current. Every movement is independent, but all of them sum up to give a general picture of incredible complexity. So it is in the universe. The rotation of the Earth, rotation around the sun, the rotation of the solar system around the center of the galaxy, the movement of the galaxy in the local group, the movement of the local group in the cluster, the movement of the cluster in the supercluster. All this adds up. And if you calculate your true speed relative to the cosmic microwave background radiation, the remnant of the Big Bang, you get an incredible figure. You are rushing through the universe at a speed of more than 600 kilometers per second. And all this rotation, all this movement began then, in those first moments when the universe was born, when the quantum foam of space-time gave birth to the first fluctuations. These fluctuations grew, intensified, and turned into matter inhomogeneities. Inhomogeneities became swirls. Swirls became the rotation of galaxies. Rotation is the signature of the universe, its autograph on every cosmic object from the smallest particles to giant clusters of galaxies. Everything rotates, everything moves, nothing stands still. And this is beautiful because rotation is life. A static universe would be dead. Nothing would happen in it. Stars would not be born. Planets would not form. Life would not arise. Rotation creates dynamics, generates changes, gives the possibility for evolution. The Earth rotates, and this creates the change of day and night. Day gives energy, night gives rest. This rhythm is fundamental for all terrestrial life. Plants use the light cycle for photosynthesis. Animals adjust their activity to the change of day and night. Humans sleep at night and are awake during the day. The Earth rotates around the sun, and this creates the change of seasons: spring, summer, autumn, winter. Every season brings its own conditions, its own temperature, its own humidity, its own day length. And life has adapted to these cycles. Plants bloom in the spring, animals reproduce in the summer, nature prepares for winter in the autumn, and freezes in the winter. These rhythms are written into our biology at the deepest level. Our genes, our cells, our organisms are tuned to the rotation of the Earth. We are children of a rotating planet, and in some sense, our very existence is a manifestation of cosmic rotation, an echo of those ancient swirls that once arose in the primary universe. Rotation gives us a future. As long as the Earth spins, as long as the sun shines, as long as the galaxy exists, life can continue, can develop, can become more complex, more diverse, can spread across the planet, across the solar system, across the galaxy. Someday, perhaps, we will leave the Earth, fly to other planets, to other stars. We will build space stations, orbital cities, and they will all rotate because rotation creates artificial gravity, gives a sense of weight in weightlessness, and allows living and working in space just like on the surface of a planet. We cannot escape rotation. It is too fundamental, too deeply written into the structure of reality. Rotation is the language the universe speaks. This is the music of the spheres that ancient philosophers dreamed of. Only they thought of harmonic sounds created by the movement of planets. In fact, the music of the universe is gravitational waves propagating from rotating black holes. This is the whisper of space-time trembling from the movement of massive objects. And we have learned to listen to this music. Gravitational wave detectors first caught a signal from the merger of black holes. Two black holes rotated around each other, drew closer, and accelerated. In the final moments before the merger, they rotated at an incredible speed, dozens of revolutions per second, and each revolution created a wave in space-time. This wave spread through the universe, passed through galaxies, through the void of intergalactic space. After billions of years, it reached the Earth. And here, in a detector built by humans, it created a tiny tremor, changing the distance between mirrors by a fraction of a proton's diameter. No, we caught this tremor, recorded it, turned it into sound, and heard the voice of the universe. The rotation of two black holes turned into sound resembles the chirping of a bird. The frequency grows, reaches a peak, and breaks off. This is the moment of merger. Two black holes became one. The rotation joined. This confirms everything we talked about. Rotation is conserved, it is transferred, combined, transformed, but does not disappear. The new black hole born from the merger rotates faster than either parent. It inherited all their angular momentum and will carry it further for billions of years until it swallows another black hole or evaporates eventually through quantum radiation. Rotation is eternal, and this gives hope. As long as the universe rotates, it is alive, it is dynamic, it changes. Which means everything is possible. Life is possible, intelligence is possible, knowledge is possible, the future is possible. We stand on a rotating planet and look at a rotating galaxy and understand that all of this is part of one great dance. A dance that began billions of years ago and will continue for billions of years in the future. A dance in which every particle, every star, every galaxy plays its role. And we dance too. whether we want to or not, because we are part of the universe, we are its children, and rotation is our legacy. Thank you for being with us on this journey through the cosmic waltz. See you among the stars.